Welcome to lecture number 16 of my series on thermodynamics. Frankly, when I finished talking about entropy in lecture number 15 of this series, I had thought that I would draw an end to the series there, because all the major topics that are really important in basic thermodynamics had, to my mind, already been covered. However, there have been several requests on the further topics from viewers after that, and discussions with my colleagues and friends have also convinced me that there are other important issues in the next few topics which are also usually not that properly covered in most courses. So here goes. This is the next part of the series, which I hope will be shorter than the previous one. In this particular lecture, we are going to take a look at first how to combine the first and the second laws of thermodynamics. And for that, of course, we need to remind ourselves what the first law and the second law are. I'm not going to go into the basics of the thing because we have already defined before that the first law really means that it is an experimental fact that work done under adiabatic conditions is actually path independent, from which you can define something called the internal energy and so on. The final form of the first law, the one we arrive at, which really is the definition of heat, is of this form: delta U, the change in internal energy of a system, is equal to Q plus W. Here Q is the heat energy flowing into the system, and W is the work done on the system. In books which use work done by the system as W, this equation would have read delta U equals Q minus W. The infinitesimal version of this equation is du equals d cross Q plus d cross W. And let me remind you that there is a basic difference between the differentials that you see on the two sides. U is a state function, a function which depends on the points in thermodynamic space, phase space, and du is the actual differential of that function. So there is a function u whose differential we are talking about on the left hand side. On the other hand, there is no q function of the thermodynamic state, which is why the amount of heat absorbed when you go from one state to another depends on the path, and it's not dependent only on the states. And because there is no such thermodynamic function Q, neither is there a thermodynamic function W. These are not actual differentials. These are infinitesimal quantities, but they are what are called imperfect differentials, and the cross on top of the D is meant to show that. Now, specifically, if you are dealing with a quasi-static frictionless process in a hydrostatic system, a system where the sole means of doing work were through external pressure, d cross W will be minus pdV. The minus sign here simply says that we are talking of work done on the system as positive, and when the system contracts, that is dV is negative, the external force actually does work on the system. That is why you have a minus sign here. The important point is that if you are dealing with a quasi-static frictionless process, then the external pressure and the internal pressure balance each other out at every stage, and so this P really is the internal pressure of the gas itself. And of course, for such a process, we can modify our first law, the infinitesimal version, to read du equals d cross Q minus pdV. Now, a special case of this is when you carry out a process in constant volume, then pdV term, the work done term in a hydrostatic system, is 0. So there delta U is the same as Q, or infinitesimally du is the same as d cross Q, which for a constant volume or isochoric process is given by the heat capacity at constant volume Cv times dt, the change in temperature. So when volume is held fixed, del U del T at constant volume, the partial derivative actually is nothing but the heat capacity at constant volume Cv. This is the result that we will use several times later. Now for the time being, let us go on and talk about the second law. Once again, this is going to be a very quick recap of what we have already said before. The Clausius inequality, which we proved after stating the second law in various different forms, turns out to be the following. If you carry out a cyclic process involving a system, then the ratio d cross q by t integrated over the entire cycle is something which is less than or equal to 0. We had shown that this is actually equivalent to the standard versions of the second law, like the Kelvin-Planck statement or the Clausius statement. And specifically, if the process is reversible, you can run it in both directions, which means d cross q by t's cyclic integral will be less than or equal to 0, and minus d cross q by t's cyclic integral, which is the corresponding result for the reverse cycle, will also be less than or equal to 0, and therefore the only possible choice there is d cross q reversible by t, when you integrate it over a complete cycle, must give you 0. And that actually tells you that although d cross q is not an exact differential, neither is d cross q over t in general, but for reversible processes, d cross q reversible over t is an exact differential. There must be a function which we call the entropy S, whose differential is d cross q reversible by t. So this helps us to define S through its differential. ds is d cross q reversible by t. Now, one immediate application of this combined with the Clausius inequality is the following. If you consider a process which a system undergoes from I to F, we are not claiming any special feature for this process. This could be any process where the system is taken from a state I to a final equilibrium state F. And then let us make this into a cycle by coming back from F to I along a reversible path. This is something we always do. So if you look at this whole cycle and apply Clausius inequality to this, what we get is 0 must be greater than or equal to the cyclic integral of d cross q by t for this whole process. And you can of course break up this cyclic integral into two pieces. From I to F, d cross q by t along our original path, plus from F to I, d cross q reversible by t along the reversible path. Now these two must add up to something which is either 0 or less than that. Now we can easily take this to the other side with a minus sign. But remember, this is a reversible process, so this quantity with a minus sign is actually the d cross q reversible by t calculated for the reverse process, which is a process which takes you reversibly from I to F. So what we get here is the d cross q by t integral from I to F, the original black path here, is less than or equal to d cross q reversible by t from I to F again along this path, the reverse of the path that has been drawn here, and that is nothing but the increase in entropy when you go from I to F. This side has nothing to do directly with entropy, but when you integrate d cross q reversible by t from some initial state to the final state, you always get an increase in the entropy. So delta S is SF minus SI. Now this tells you this very important result, that this integral is always less than or equal to the entropy increase of the system. In particular, if the original process, the one which takes you from I to F, were adiabatic, d cross q would be 0 for that process, and you will end up with the result that delta S is greater than or equal to 0. So the entropy of a system always increases for an adiabatic process. Or if the process itself were not adiabatic, you can always take the surroundings of the system and the system together and calculate the entropy change of what is called the universe, which of course would be an adiabatic system. It cannot interact with something outside simply because there is nothing outside which it interacts with. And we end up with this very famous restatement of the second law, that the entropy of the universe always increases. A less grandiose statement would be that the entropy of a closed system, a system which does not exchange energy with the outside, always increases, or at best stays the same. The final thing, of course, happens when you're talking of a reversible process. Going back to this equation, what you can see is that for an infinitesimal process, this actually tells you that d cross q by t will be less than or equal to ds, and that means d cross q is less than or equal to TdS. Remember, capital T, the absolute temperature, is greater than 0 for any equilibrium process or quasi-static process, and therefore d cross q by t less than or equal to ds translates to d cross q less than or equal to TdS. Now, if we use this in our first law, here we are combining the first law with the second, du, which was equal to d cross q plus d cross w. With this input from the second law, you can write du as less than or equal to TdS plus d cross w. Now, for a reversible process, d cross q must be equal to TdS, for the simple reason that you could run the process in reverse and then this same inequality would have to hold in the other direction. Minus d cross q will have to be less than or equal to minus TdS, or d cross q would have to be greater than or equal to TdS at the same time. The only way that happens is d cross q is exactly equal to TdS. So for a reversible process, the combination of the first law and the second becomes du is TdS plus d cross w. And remember, if you're dealing with a hydrostatic system, then a reversible process would also mean that the process would have to be quasi-static and friction-free, and therefore d cross w can be replaced by minus pdV. So for a hydrostatic system undergoing a reversible process, we can derive this result that du is TdS minus pdV. This is going to be our version of the combination of the first and second law. Of course, restricted only to hydrostatic systems. If the system were non-hydrostatic, if there were other means of doing work on the system, you would have to modify the minus pdV term into some other form. For the time being, we are going to stick to reversible processes in a hydrostatic system. Now, this combined version of the first and second laws of thermodynamics, du equal to TdS minus pdV, is often a bit confusing for people. The confusion stems from the fact that this relation has been derived for an infinitesimal reversible process in a hydrostatic system. The derivation is for an reversible process. But does this equation work only for reversible processes? The answer is no. This is where many people get this confused. This equation actually holds for any infinitesimal process that is occurring in a hydrostatic system, at least any infinitesimal process where you are going from one equilibrium state to a neighboring equilibrium state. So for two neighboring points in our thermodynamic state space, given here, which has thermodynamic coordinates given by u, t, s, p, v, and a neighboring point where these same quantities change a bit, u becomes u plus du, t becomes t plus du, dt, sorry. So t becomes t plus dt, s of course becomes s plus ds, p becomes p plus dp, again a mistake here, v becomes v plus dv. The important point is that these quantities, both for the original state and the next neighboring state, depend only on the two states involved, not on the path taken from here to here. So if you were going from here to here along a reversible path, you would get du equals TdS minus pdV. But since these quantities do not depend on the path at all, the result du equals TdS minus pdV must be valid for all paths. It must be a mathematical statement about the way u depends on S and V. In particular, if you were to express U as a function of S and V, then du would definitely be the partial derivative of U with respect to S at constant V, ds, plus del U del V at S, dV. This is nothing but the standard mathematical formula for the total derivative of a function of multiple variables. And comparing this with du equals TdS minus pdV simply tells you that the temperature of a system is nothing but the partial derivative of its internal energy with respect to its entropy at constant volume. Similarly, if we were to take a partial derivative of the internal energy with respect to volume at constant entropy, you are going to get minus P. These are statements about the functional dependence of U on the quantities S and V. This is completely independent of the path which is being followed. As a result, let me stress once again, as long as you're dealing with infinitesimal processes or infinitesimally neighboring points in the thermodynamic state space of a hydrostatic system, du equal to TdS minus pdV will remain valid. If you're talking of some other kind of system, the minus pdV would have to be replaced by the corresponding infinitesimal work done. Now, notice that if you knew U as a function of S and V, this would yield T as a function of S and V, this partial derivative. This one would yield pressure as a function of S and V. And then you could perhaps say decide to eliminate S between the two. And then you would get T as a function of P and V, which is nothing but the mechanical equation of state. Now, it might also be quite possible to express U as a function of other variable pairs, like say temperature, pressure, or pressure and volume, or S and T, or some other choice. For example, if you decided to write U as a function of T and P, you would be able to write du as del U del T at constant pressure dt plus del U del P at constant temperature dP. Again, no physics is involved here. This is just a mathematical statement about how a function of multiple variables change. Similarly, if you were to write U as a function of P and V, you could write this expression down. I put in an etc. here without lengthening the list because you could actually take any pair of arguments here, write U as a function of that, and get an expression for du. Now, what is important is that the partial derivatives that you see in this expression, del U del S at constant V, del U del V at constant S, which are actually T and minus P respectively, and these partial derivatives must be related to each other. And let me just show you how you can figure out the relationship. Suppose, instead of either of these two pairs, you wanted temperature and volume to be your independent variables. That's always possible. Then you would write du in this form, del U del T at constant V dt plus del U del V at constant T dV. But it has to be TdS minus pdV. But in order to relate this to this, what you need to do is, you notice the dV is already here. You don't really have to do much to change this. But this ds, you have to write in terms of dt and dV. But that's easy. Think of S as a function of T and V. Then ds would simply be del S del T at constant V dt plus del S del V at constant T dV. Is taken this ds, put it in this term here. And now by collecting together coefficients of dt and dV, I can immediately write this down. And by comparing this with our original version, purely mathematical statement of how du should look like if you were expressed as a function of T and V, you would get that del U del T at constant volume must be T del S del T at constant volume. Del U del V at constant temperature must be this factor, T times del S del V at constant temperature minus P. These equations are going to be pretty useful in dealing with various complicated problems, some of which we are going to take a look at in later lectures. Now, we must clarify another point which actually is critically important and will help us understand many new concepts in later lectures. It is often said that because du is TdS minus pdV, U must be a function of S and V. But let us take a look at this. Exactly what does this statement really mean? After all, you could write du as x times dt plus y times dv, x and y being these quantities. So why don't we say u is a function of T and V? Of course, we could do that. We could eliminate entropy from whatever function of u as S and V you have. Remember, if you know u as a function of S and V, then temperature can be simply figured out from there. And therefore, what you're going to get is temperature as a function of S and V. Now, between this equation and this equation, I can eliminate the entropy in favor of the temperature, and you will get u as a function of T and V. So it seems that saying that u is a function of S and V is just a whim. I could have just as well said u is a function of T and V. But there is actually deeper meaning behind the statement that u should be expressed as a function of S and V. And those of you who have done classical mechanics, analytical mechanics, must have seen this before. In another topic, the Lagrangian of a system is written down as a function of its position and velocities. Whereas the Hamiltonian, which is del L del Q dot times Q dot minus L, I'm just using one single coordinate for the time being, would come out to be a function of Q and Q dot as well from the calculation. But you have to actually trade the Q dot for P, which is this del L del Q dot. Right? Hamiltonian is a function of Q and P. And we keep on saying things like L is a function of Q dot, H is a function of Q and P. And very often we use an expression, the fact that dH can be written down in terms of something times dq plus something times dp to justify this. However, as I've just argued, you can easily rewrite any function of two such variables by eliminating one of the resulting dependent variables from them and write it in terms of some other variables, which you have done here. Now, I will not spend more time talking about the Lagrangian and the Hamiltonian because this is not germane to the topic right now. But let me also tell you this. The sense in which u is a function of S and V rather than a function of T and V is the same sense in which Hamiltonian is a function of Q and P rather than Q and Q dot. Why is that the case? We will learn about that later when we talk about how to change variables from the preferred pair to something else. But for the time being, let us focus on why is this pair of variables S and V, why is this pair the actually preferred pair of arguments for you? To see this, we will have to. But before we start talking about that, let's make a small correction, or rather an extension. The equation that we had written down, du is TdS minus pdV, is going to be our central equation for this lecture. But this is really valid only for a closed hydrostatic system. The hydrostatic part we have already talked about. The minus pdV comes in because hydrostatic work is the only kind of work available. However, the important thing here is that we are assuming that this system is closed, which is something we have been assuming without even stating it so far. This is one in which n, the amount of matter, the number of moles, does not change. If we allow n to vary, we have to add one more term to this du. Apart from u changing because of the change in entropy by TdS, or changing because of the change in volume by minus pdV, there will be an additional term which will tell you how much u will change if you were to keep S and V fixed but add particles to the system. Change the n. So the full result will be du is TdS minus pdV plus mu Tn. And so we will have to modify our previous statement slightly. Temperature is actually del U del S, not only at constant V, but at constant V and constant N. This constant n part was taken to be obvious so far because we were talking only about systems where the amount of particles or amount of molecules or number of molecules in the system does not change. Now, here we are going to express u as a function of Svn. If you do that, this partial derivative will be easy to calculate and temperature will come out as a function of Svn. Pressure, very similar. It's again minus del u del v, but this time you have to worry about keeping both S and N constant. And this pressure will again come out to be a function of Sv and N. And finally, the only new thing will be this mu, this coefficient here, is del u del N at constant S and V. So this is basically the rate at which the internal energy of a system changes if you increase the number of moles in it without changing the entropy or the volume. This mu is called the chemical potential. The reason for this name will be clear once we talk about chemical reactions and the role mu plays there. But the important thing is the most usual kind of system where number of moles of a system of a particular component changes is actually, it is easy to see that this quantity mu will play an important role in chemical reactions, because in chemical reactions the number of moles of different constituents of a system changes. Another place where mu will play a very important role in physics as opposed to chemistry would be during phase transitions, where the number of moles of one phase will change into the number of moles in another phase. So when we talk about those situations, phase transitions or chemical reactions, we will have to pay a lot of attention to the chemical potential. However, for most of the part, we will sort of ignore the mu dn term simply because we will be dealing with closed systems more often than not. For the time being, at least for the duration of this lecture, we are not making this restriction to closed systems, so the mu dn term should be taken into account in u. Now, the claim that we are making here is the following. If you express u as a function of the entropy, the volume and the number of moles of the constituent system, here we are assuming that there is only one constituent of this particular system. So there's only one n to worry about. Of course, if you had multiple components making up the system, you would have to deal with n1, n2, n3 and so on. The claim is this u of Svn has complete thermodynamic information about the system. In other words, as we have already seen, if you know this function, you should be able to find out temperature, pressure, chemical potential as functions of entropy, volume and number of particles or number of moles, and eliminate variables as you want, maybe eliminate S to write T as a function of P and V and so on, to re-express this as necessary. So this is the important point here. Knowing u as a function of S, V and N gives you as much thermodynamic information about the system as you can possibly get. Just to show that, let's consider a particular example. Suppose, maybe by experiments or maybe by some other theory, you have found out that for a particular system, u Svn is given by this particular form. Capital A, which is a constant, times n, the number of moles of the constituents, times capital B by n to the power A, multiplied by exponential of small b s by n. So small a and small b along with capital A are constants here. Now one very important point. This form may seem pretty unfamiliar and maybe quite complicated to you, but it definitely conforms to one very important property which the internal energy must have. Note that both u, the function that we are looking at, and the arguments Sv and N share a very important common property. They are all extensive variables, which means if you scale up the system, each of these variables change by the same factor. What this means mathematically is that if you change n to lambda n, v to lambda v and s to lambda s, u should also become lambda u. Let us check whether that happens. If you did that, capital A of course stays the same. This n becomes lambda n. Here you have lambda b by lambda n, the lambdas cancel. Inside the exponential you have b lambda s by lambda n, the lambdas cancel once again. So you're left with one overall factor of lambda times u, which is exactly what an extensive variable should behave like. So this form that we have written down is at least consistent with the fact that the internal energy of the system is an extensive property. This will turn out to be quite a useful thing, as you will see later in this lecture. Now, first, if you start with this and try calculating its temperature. Temperature would be differentiation with respect to S. Of course, you are differentiating an exponential, which is pretty easy to do. The only thing that will happen is b by n will come down as a factor. So this is just going to be b by n times u. I've written u here simply as a shortcut instead of writing the whole thing. But as I can see, temperature is coming out as a function of S, V and N. Or of course you can rewrite this in the form u equals 1 over b nt. What about pressure? Pressure basically means you have to differentiate with respect to v, and there's a power of v here, v to the a. And when you differentiate that, it becomes a v to the power a minus 1. So basically, differentiation with respect to v multiplies this whole expression by a over v. And because of the minus sign, you get minus a by vu. And you can immediately rewrite this to pv equals minus au, which is minus a by v nt. If the first equation did not do this for you, the second equation definitely should suggest that this is a familiar system, at least for choices of small a and small b. If we choose minus a by b to be r, then this becomes just the equation of state of an ideal gas, PV equal to nRT. And well, for a monoatomic ideal gas, I'm pretty sure most of you are aware that the internal energy works only 3 by 2 nRT. So 1 over b can be chosen to be 3 by 2 nr. With that choice, a by b equals minus r and 1 by b is 3 by 2r, which of course means that a comes out in minus 2 by 3, gives you very familiar forms. PV is nRT and U is 3 by 2 nRT. These are the familiar forms valid for a monoatomic ideal gas. So this rather complicated looking equation that we wrote down, this function of U as a function of S, V and N, actually gives you something very simple as a physical system. It's really the basic equation for a monoatomic ideal gas. Now, notice that by this process, once you have chosen small a and small a properly, by this very process, what we have really done is we have found out the thermal property, that is U is 3 by 2 nRT, which would mean Cv, the heat capacity at constant volume, diluted at constant V is just 3 by 2 nR, as well as the mechanical property that the pressure is related to the temperature by nRT by V. Any other property that you want of the ideal gas, any other thermodynamic property is essentially encoded here. So this is actually called the fundamental equation. Well, calling it the equation of state may confuse people with other things. We had better just call it the fundamental equation. This is the fundamental equation for a monoatomic ideal gas. Once you know this function, U as a function of S, V and N, you know everything that is there to know about the system. Now, by contrast, we could have started with U equals 3 by 2 nRT. That can only give us partial information. For example, what this will tell you is Cv is 3 by 2 nR. But what it will not tell you is that Pv must be nRT. This information is completely absent from this equation. On the other hand, Pv equals nRT, the so-called equation of state, or strictly speaking, the mechanical equation of state of an ideal gas, will not tell you how U depends on temperature. However, if you give U as a function of S, V and N, as we have done here, ultimately you end up with all thermal and mechanical properties. This is basically why we say U is a function of S, V and N. You can of course write U as a function of T, V and N by eliminating S. or TpNN by eliminating volume and bringing in pressure. You can do all that. However, the important thing is all of this will not give you complete thermodynamic information of the system. The only one which will give you complete thermodynamic information is U expressed as a function of S, P and N. And that function is what you call the fundamental equation for the particular system. This of course is a fundamental equation for a special kind of system. For a different system, the fundamental equation will of course change. Now, once we have said this, the natural question to ask is, where can we get the fundamental equation from? If it has all this information, it would be important to know where we can get this from. And the answer is not from thermodynamics. Can either get it from experiments or from some more fundamental theory. Let me just illustrate quickly how you could get the fundamental equation for the ideal gas that we had written down a while ago from experiments. Experimentally, we know the following. U is 3 by 2 nRT. So let's forget all about the particular form of U that we had learned about earlier, at least for the ideal gas. Let's just look at this as an exercise of using experimental results that we know to find out what U is. Experimentally, for a dilute gas, which is a good approximation for an ideal gas, made out of monoatomic molecules, we find that U is given by 3 by 2 nRT, at least at high enough temperatures. So U is given by 3 by 2 nR del U del S at constant V and N. All we have done is express temperature as del U del S. But this, at least at constant V and N, we can write this equation as du over U as simply 2Ts over 3 nR. This is just a rewrite of this equation. And this can be easily solved to give you U is a constant times e to the power 2s by 3 nR. The only catch here is the constant is a constant under these conditions. Remember, we are working here with V and N held constant. So any function of V and N can serve as a constant here. There is really nothing but the constant of integration that we have. Again, PV equal to nRT by replacing P by minus del U del V at constant S and N, and replacing nRT by 2/3 U from the previous equation gives you a very simple result. The du by U must be minus 2/3 dV by V. And this will tell you that apart from this factor, this FVN must have the following property. FVN must be V to the minus 2/3, essentially from here, times a function of N and N alone. So combining these together, we get U is some function of N times V to the minus 2/3 e to the power 2s by 3 nR. Finally, you have to use the fact that U is an extensive variable, which will tell you that Gn must be N to the 5 by 3 times some constant, independent of N, S or V. So this is what your final form becomes, which is exactly the form we had talked about before with the special values for A and B, small a, small b put in. As we said, this is how we would find out the fundamental equation for a thermodynamic system starting from experimentally obtained results. The other approach would be use a more fundamental theory, like a theory which talks about the microscopics of the thing. In statistical mechanics, this is something which is a quick aside. We are going to not talk about statistical mechanics, at least in this lecture or this series of lectures, but very quickly, in statistical mechanics, we can use what is called a macrocanonical ensemble to calculate the quantity W, which is a function of U, V and N. W is basically the number of ways in which you can get, or number of microstates, which a system with total energy U, volume V and number of moles N can be in. And then use Boltzmann's famous relation S equals Kb log W to calculate S as a function of U, V and N. And this can easily be inverted to get U as a function of S, V, N. So the microcanonical ensemble is a way to go if you want U as a function of S, V and N. This would be a calculation which involves the microscopic nature of the system. Let me point out that the fact that you cannot get the fundamental equation from thermodynamics alone should be easy to understand. After all, thermodynamics gives you broad sweeping results which work for all systems. If you could actually get the fundamental equation for a particular system from thermodynamics alone, that would essentially mean that all systems would end up having the same fundamental equation or similar fundamental equations, and all systems would essentially behave similarly. And then all the variety that we see around us would simply be lost. That, of course, doesn't happen. Thermodynamics doesn't tell you exactly what the fundamental equation is. Given the fundamental equation, you can use thermodynamics to find out all the properties that you need about the system. Now, one thing we had not done in our calculation earlier was finding out the chemical potential. Now, if you start with our form for the U, which remember was A V by n to the power small a times capital N exponential B times S over N. Then for the chemical potential, if you do this partial derivative with respect to N, there's an n to the power 1 minus a as a factor. This will give you 1 minus a U by N. When you differentiate this term, keeping the rest intact. If you differentiate this term, you will get minus Bs by N squared times the whole thing. So this is what mu works out to be. And if you take u over n common, this is the expression that you get. And putting in the values of small a and small b, it worked out, you get mu as a function of SVN given by this. Of course, you have an u stuck here, you can always replace the u by this expression to get the final result. Now, what is more illuminating here, and perhaps a bit surprising, is that you can rewrite this intermediate stage in a rather interesting fashion. If we were to multiply both sides by capital N, you get mu n is 1 minus a into u minus bs by n into u. However, these quantities that you get as a result, minus au and minus bu by n, should be pretty familiar. Minus au is nothing but p times v, and this factor here, bu by n, is t. This is something we had already worked out a few moments before for this particular fundamental equation. So at least for this particular fundamental equation, we see that u is Ts minus Pv plus mu n. So this, it has been derived only for this particular fundamental equation here, but you might suspect that this is really not an accident. Something this neat should not follow by accident. Indeed, this is not a property only for this particular fundamental equation. This is a property, a result which is valid for all fundamental equations. To see that, let's start with the basic fact that u is an extensive function of extensive variables. So if you were to think of lambda copies of the system, entropy, volume and number of particles will all pick up an extra factor of lambda. So S will become lambda S, V will become lambda V, N will become lambda N. So I have u as a function of these three arguments must be the u for the scaled up system, lambda times u SVN. Now, let us differentiate both sides of this equation with respect to the parameter lambda. So here, on the right hand side, it's very simple because lambda is there only in one term, overall multiplier. So if you differentiate the right hand side with respect to lambda, you just get USVN. The left hand side is more complicated because here you have three arguments, each of which actually depend on lambda. So this really should be del u, del the first argument, times del lambda s, del lambda, which is just part of the chain rule. So you just get an S here. Similarly, from this term you get V times del u del lambda V, and finally you get N times del u del lambda N. And here of course this u has partial derivatives which will be functions of three arguments, where this left hand side has to be evaluated is when lambda n. For lambda S, lambda V and lambda N. But now what we can do is specialized to the special case where lambda is 1. Then what you get is this thing becomes del u del s, and what we had not written down before is that this is, of course, derivative with respect to the first argument, keeping the second two fixed. For lambda equal to 1, the other two arguments such as v and n. Similarly, this is del u del v at s and n, del u del n at s and v. But notice that these three partial derivatives are nothing but temperature, negative pressure, and mu. So, in general, for all systems, and this is the consequence simply of the fact that u is an extensive function of variables which are themselves extensive, u has to work out with Ts minus Pv plus mu n. This very important relation is called the Gibbs-Duhem relation. We are going to make use of this later quite extensively. Notice one strange thing that is a consequence of this. If you take the differential of both sides, du works out with TdS plus S dt minus PdV minus VdP plus mu dn plus n dv. But we have written down one part of each of these differentials, products, TdS minus PdV and mu dn, here in red, the rest in blue. You can easily see the reason why. TdS minus PdV plus mu dn is actually du. That is our combined first and second law, extended with changing number of particles as well. So, TdS minus PdV plus mu dn would have been du in itself. Adding these extra pieces, S dt minus VdP plus n dmu, does not change that. And that means that S dt minus VdP plus n dmu, so there's a mistake here, which has to be corrected. N dmu is 0. This equation is also called the Gibbs-Duhem relation because this basically is a direct consequence of this. This again is a consequence of the fact that the entropy, volume and number of particles and the internal energy are all extensive variables, and we will find this to be pretty useful when we need to talk about changes in, say, the chemical potential. d mu works out to be from this simply minus S over n dt plus V over n dP. So how does chemical potential change when you change the temperature and pressure of the system? Can be figured out from here. Something which will be quite useful when we talk about phase transitions or chemical reactions. But all that is for a later lecture. Today we have investigated the combination or bringing together the first and second laws and how that makes important mathematical claims about the relationships between U and various other thermodynamic quantities. In the next lecture, we are going to see how you can change the variables S, V, N to other variables and still maintain the complete thermodynamic information which the fundamental equation has. In other words, how we can go over to a different set of variables and still get a fundamental equation which will tell you everything about the thermodynamics of the system. Let me just end by saying one thing about dynamics, Lagrangian and Hamiltonian, simply because I mentioned that before. The fact that Hamiltonian has to be written down as a function of Q and P and not Q and Q dot is because that's the only way you can change the variable from Q dot to P and still retain complete dynamical information. We will see how to do something similar in thermodynamics. How can we trade in, say, the volume for something else, in particular the pressure, or the entropy for the temperature, and get another fundamental equation which will give you the entire thermodynamic. We will keep the thermodynamic, which will give you which will retain complete thermodynamic information. But that we'll have to wait for the next lecture. Bye for today.